Okay, next section, section 2, is forces in motion, and there's lots of it. So we've got some notes of a student, and they want to look at stopping distance. We know that's the thinking distance, and that's the braking distance. So they must have pressed the brake there. So what's the reaction time? Well, it's this bit here, and we can read off 1 second. It says use the diagram to calculate the braking distance. Well, we can see that's this bit here, and we're just working out the area. So I'm going to get rid of my doodles, and we can see, well, we've gone from 1 to 4.5, so that's a change of 3.5, and we've gone from 0 to 35, that's a change of 35. So we've got 3.5 along the bottom and 35 up the side, and that would give us the whole of that area, but we only want the triangle, so we have to divide by 2, because you will have learned that the area of a triangle is half BH. Okay, so 3.5, the time difference, multiplied by 35, the speed difference, divided by 2, gives us 61.25 meters. Next one, what might affect a driver's reaction time? So tiredness and drugs, and then we've got to say what would it do to their reaction times? It would increase them, all right, which is not a good thing. It says, why might Tesla's autonomous driving cars reduce injuries? Well, the crucial thing is they've got a computer. They're autonomous, so they have no human reaction times. So there would be no human reaction times, and therefore the thinking distance will be less. Don't talk about the braking car. Having a computer is not going to make the brakes go any better, but it's the thinking distance. Explain how a wet road might affect the braking distance. Well, we know that that's going to mean I need more braking distance, and that's a bad thing. I'm more likely to hit someone. And then we've just got to say that a wet road has less friction. So it would increase the braking distance. That's not a good thing. So as there is less friction between the tyre and the road. Next one, use the graph to determine how far Colin had travelled after 500 seconds. I'm just going to find where seconds are. There's 500. I'm going to read up and read across. You can see it's 500. He's gone 500. Next one, find out the instantaneous speed for section A. Well, we know we're going to need shoot Donald Trump. Here's section A, and we can see we've gone from 0 to 500 there. That's a change of 500. That's this bit. Now let's do this bit. And we've gone from 0 to 400 there. Now we've got our changes. And we know that speed equals distance divided by time. There's my distance, 500, divided by time, 400. So speed equals distance divided by time, 500 divided by 400 equals 1.25. So that's a mark, meters per second. Right, the next bit's tricky. I'm going to get rid of all my doodles. There we go. So the next part, AMDIP moves at a constant speed of 1.5 meters per second. So there's his speed. It says, what was the time? So we've got to find out T. Between him and Colin to reach 750. So there's my distance. So you can see I've got to do T equals D over S. Once I've got AMDIP's time, I then compare it to Colin, and Colin is on the graph. All right. So first job, T equals D over S. 750 divided by 1.5 is 500 seconds. Now let's go and find Colin. So Colin, for 750 meters, and again we're looking here, took 680 seconds. So we know AMDIP took 500, Colin took 680, and then we just take those away. 680, take away 500 is 180 seconds. Okay, this next one you're really good at, you've been ace at. So how can I do an experiment with a ramp to measure the speed? So use a ruler to measure the height of the ramp. Change the height and then give 10, 20, 30, 40, 50 centimetres. Next part, use a ruler, give your measuring equipment to measure a distance at the end of the ramp, like I've done there. Next part, use a stop clock to measure the time over that distance. Speed equals distance divided by time. That's quite easy. Next one, a car accelerates from 2 to 20. So that's U, that's V, and it's an average acceleration of 0.9. What is the time taken? And it tells you the time equals the change in velocity, so the difference between 2 and 20, and the acceleration. Or another way of putting it, A equals V minus U over T, or T equals V minus U over A. So t equals v minus u. So 20 take away 2, take your 2 speeds taken away, 18, and divide by the acceleration. It took 20 seconds. The next one, a car is travelling at 22 meters per second. It applies the brakes. That's it starts. That's u, 22. And it comes to a stop. So v must equal 0, and it gives me the deceleration. It says use v squared minus u squared equals 2ax. So if I just write that by the side, v squared minus u squared equals 2ax. Well, I want to find x, and I've got 2 and an a times by it. So that's going to have to go underneath. I'm going to have to divide both sides by 2a to get x on its own. So there we go. X equals v squared minus u squared over 2a. Now let's pull the stuff down. It finished at 0, 0 squared, minus 22 squared, that's what it started at, divided by 2 lots of 1.4. That comes to minus 484 divided by minus 2.8 equals 172.9. And the last part, what is the difference between speed and velocity? Speed is a scalar, velocity is a vector. And if you're struggling with that, I'd like both if you can, but it's velocity is speed with a direction. And I think that's the end of the forces section. It is.